We'll now learn about dynamics. Dynamics is the backbone of Newtonian physics, so it is very important that you understand this topic. These are the learning outcomes, and we will revisit them as we go along during the topic. Now, what is dynamics? How is it related to what we have studied so far? Okay, in chapter 2, we learn about kinematics. Kinematics is a study of motion. That is about displacement, velocity, and acceleration. And it is a study of how things move. And dynamics is study of what causes motion. We can say that it is actually a study of why things move. We'll now begin with Newton's first law of motion. As a kid, I'm sure you already know this. A ball at rest remains at rest unless a net external force acts on it. Is the force by the dog an external force? Yes, because the dog is an external body. The ball is acted by the dog. Now, is it possible that the ball travels with constant velocity? That means the speed is constant and it moves in a straight line. What happens is this: when the ball is in the air, its weights pull it downwards. So a net external force, in this case the weight, acts on it to prevent it from going in a straight line. Right? So every object continues its state of rest, right? Like a ball remain at rest, unless the net external force acts on it to change that state. And every object continues in its constant speed in a straight line, unless a net external force acts on it to change that state too, which is why the ball did not move in a straight line. So now we can generalize the ball to any object and form this first law. Note that the force needs to be a resultant force or net force, and it must be an external force. You need to memorize this first law and you must be able to state it in exam. Okay, now let's check your concept. Watch the video and answer the questions.
Yeah.
Now, what intervention is required to make the ball move in a circle? There is a net external force, a force from the hammer. As it hits the ball, it changes the direction of the ball's velocity, which makes it move in a circular manner. At the end of the video, you see that the force is removed and the ball moves in a straight line. And this is in accordance to Newton's first law. When there is no force acting on the body, it should continue its state of rest or continue in a constant velocity. Now, that is also called the law of inertia, the Newton's first law of motion. Let's check our concept. Why does an unstrapped passenger fall forward when a car brakes suddenly? Okay, you will know why after this video.
Ooh, that looks nasty. And
Can you see that the brakes reduce the car speed, but the passenger who was previously moving with the speed of the car, because it's moving with the car, before the car speed brakes, it is still moving with the original speed of the car. So the passenger continues to move forward according to Newton's first law, since there is no net external force to change his state of motion. Until he hits something, then he will stop. This natural reluctance for a body to change its state of motion, that is, the passenger continue moving forward even though when the car is braking. This is called inertia. Right? And mass is the property of a body which resists change in motion. The larger the mass, the greater its inertia. In other words, we can measure the amount of inertia using mass. If the object has a larger mass, it is harder to change its state of motion. And this is learning outcome B. So understanding that mass is property of a body which resists change in motion. At A level, you do not say mass is the amount of substance in the body. You should say mass is a measure of the amount of inertia. Okay, now we look at first law in more detail. So first law state as follow. You can read for yourself, it's in the box. Right, notice that net external is of different color. So that is my emphasis. A net external force is required to change the object's velocity. Okay, velocity is a vector, so it has a direction or magnitude. So long either the magnitude or the direction or both are changed, we say that the net external force is required. Why is net external force required? Can we have other kind of forces? When we watch this cartoon, we actually do not think much about physics, isn't it? Is it possible that the coyote moves due to the fan? Let's carry out an experiment to find that out.
This cart has a sail on it, and if it's hit by outside air, well, let's see what happens. The moving air simply hits the sail and pushes the cart forward. Now, instead of using an outside air source, this cart has a fan on it, and if I turn it on, the fan is able to drive the cart backwards, in this case, which is a really nice example of Newton's third law. The fan pushes the air forward, which drives the cart backwards. So now the question becomes, well, with the sail, air hitting it wants to drive the cart forward. Without the sail, the fan wants to drive the cart backwards. So what's the result if I have the sail and the fan both acting on the cart together? In this case, the force from the fan and the force on the sail are both applied to the cart. They are the same size but opposite in direction, so they cancel each other out. Now this pretty much guarantees that Wile E. Coyote is not going to catch the Roadrunner, and Dr. Dolittle and his friends aren't going to escape from the pirates.
Can you explain why in Newton's first law, the force cannot be internal, but must be net external forces? Okay, when the fan is switched on, the air moves and pushes the sail forward. The force by the air provides a net external force on the cart and it moves. Let's see why internal forces cannot cause a change in the state of rest or constant velocity. Now we look at the cart with the fan on it and the sail on it. There is a force on the air by the fan, and because the fan is pushing the air forward, the air also pushes the fan backwards. So there's a force on the fan by the air. At the same time, as the air is being pushed by the fan forward, it actually pushes the sail. So there's a force on the sail by the air. When you look at these two forces, one is on the fan and one is on the sail. Both are part of the cart, but they are in opposite direction. Therefore, we call this internal forces because it is acting on one body, the cart. And since the two forces are in opposite direction and they are equal in magnitude, there is no net force on this cart, right? So internal forces cannot change the state of motion of a body, only net external forces can. As we have seen from the example of the cart, internal forces are forces that are of the same type. Both of them are equal in magnitude, opposite in direction, acting on different parts of a system. Like one act on the fan and one act on the sail, but they are all acting on the cart. We will learn more about this when we look at Newton's third law later on. Right, as mentioned earlier, these forces effectively cancel each other out, resulting in zero net force, and hence no change in momentum of the system. Other examples of internal forces are tension, compression, torsion, and shear. Okay, but torsion and shear, they are not in the syllabus, so you do not need to know them. This is the end of Newton's first law.